Have you ever really thought about why a metal spoon feels so different from a wooden one? Or, why you can wrap your leftovers in aluminum foil, but not in, say, a sheet of coal? Well, today we're going to uncover the hidden rules that sort pretty much everything around us into two very distinct categories.
And it all starts with a really simple observation. A student named Anandi was watching an ironsmith at work and just wondered, hey, does everything behave like that piece of iron when you hit it? It's a great question, one you've probably wondered about too, and it's the exact mystery we're going to solve right now.
So, to get to the bottom of this, we've gathered our own little collection of materials. We've got some classic shiny stuff, a piece of copper, some aluminum, and just a regular iron nail. And then we have some duller, kind of earthy materials, a lump of sulfur, a piece of coal, and a block of wood. Let's put them to the test and see what happens.
All right, first up is a simple, maybe a little forceful test. What happens when we just hit them with a hammer? Now, this ability to be hammered into a thin sheet without completely shattering, that's a special property. It's called malleability, and it's a huge clue in our investigation. I mean, just think of the aluminum foil in your kitchen. That is malleability in action, a solid block that's been flattened into a paper-thin sheet. And boom, right away, a super clear division appears. The copper, the aluminum, and the iron all flatten out when they're hit. But look at the coal and sulfur. They just shatter into a bunch of pieces. There's a word for materials that break like that. We call them brittle. Okay, so some materials can be flattened. Got it. But what if we try to do the exact opposite? Instead of squashing them, what happens if we try to stretch them out? This property is called ductility, and honestly, it's pretty wild. It's the whole reason we can pull certain materials into these incredibly thin wires, which gives us everything from the copper wiring hidden in our walls to the fine metal strings on a guitar. And to give you an idea of just how ductile some things can be, get this, a single gram of gold, which is tiny, right, can be stretched into a wire that's 2 kilometers long. That's just an absolutely incredible property.
So for our next clue, we can put away the hammers and the stretching machines. All we need are our ears. Let's just listen to what happens when we drop our materials.
You can hear the difference right away, can't you? The metal objects make that clear, ringing sound, but the coal and the wood, it's just a dull thud. Materials that make that signature ringing sound are called sonorous. Yep, just like a big school bell. All right, for our final physical test, let's see how our materials handle the flow of energy. We're talking both heat and electricity. This one's a big deal because it has huge implications for how we use these things in our everyday lives. You've definitely experienced this yourself. You put a metal spoon and a wooden spoon in a cup of hot coffee or tea, and the handle of the metal spoon gets hot, fast. The wooden one stays cool. That's because the metal is a good conductor. It lets that heat energy travel right through it. And what do you know? We see the exact same pattern with electricity. When we use copper, iron, or aluminum to complete a simple circuit, that light bulb glows nice and bright. But when we try to use sulfur, coal, or wood, nothing. They're poor conductors, so they just block the flow of electricity. So let's just step back and look at all the evidence. Every single test we did, hitting them, stretching them, listening to them, passing energy through them, it's all pointed to the same conclusion. Our materials have basically sorted themselves into two very, very distinct groups. And here's the pattern laid out perfectly. On one side, you have the materials that are malleable, ductile, sonorous, and are good conductors. We call this group metals. And on the other side, you've got the stuff that's brittle, not ductile, sounds dull, and are poor conductors. We call those nonmetals. But the differences don't stop there. It's not just about their physical properties. These two groups also behave in completely opposite ways when they react with the world around them, especially with the air we breathe and the water we drink.
Let's take iron, a classic metal. This little experiment shows something really important about rust. An iron nail needs to be exposed to both air and water at the same time for rust to form. If you take one of those away, the rust just won't happen. And this whole process of corrosion or rusting, it's been a puzzle for people for a very long time. I mean, just look at the Iron Pillar of Delhi. It's more than 1,600 years old and has almost no rust on it, which just goes to show you how skilled ancient metallurgists were at preventing it.
Okay, now for a key chemical difference. When metals, like magnesium, react with oxygen, they form something called a basic oxide. You can think of basic as being chemically kind of like baking soda. But when nonmetals, like sulfur, react with oxygen, they form an acidic oxide, which is chemically more like vinegar. So even their chemical reactions create total opposites.
So why do we spend all this time sorting materials into these two piles? Well, because understanding this fundamental difference is absolutely crucial. We rely on both metals and nonmetals for pretty much everything in our modern world, and even for our own survival.
We tend to think a lot about metals, right? They build our bridges, our cars, our skyscrapers, but it's the nonmetals that are the quiet, essential ingredients for life itself. From the oxygen we're breathing right now to the carbon that forms the backbone of our DNA, we literally couldn't exist without them.
It's a pretty fascinating question, isn't it? It really highlights this incredible balance of materials that makes our world possible. One group gives us the tools and the tech to build a civilization, while the other group provides the actual building blocks of life. Together, they create everything we know.